Hey ChemExcel, in this video we're going to look at driving force number 2, entropy. So first of all, entropy sounds similar to enthalpy, so let's talk about how they are different. Okay, driving force number 1, enthalpy, came down to molecular stability. Okay? Which direction was exothermic, which direction made your more stable molecules. Driving force number 2, entropy, is going to be about structure versus chaos. Now some of you are thinking, those seem really similar. How are molecular stability and structure versus chaos not the same thing? All right, so first I'm going to convince you that these are not the same thing, because a very common misconception is that stable molecules are structured, but very often they're not. Structure and chaos are about, what do you think? Take a look at your context clues on the slide. All right. They're about these states of matter. All right, I want you to label your states of matter, solid, liquid, gas, as structured, kind of structured, and chaotic. Go ahead, put your answers on your paper. Did you put your answers on your paper? Hope so. Okay, here's what I've got. Solids are our structured ones. Gases would be the chaotic one. Liquids still kind of structured. We know that they're more similar to solids than they are to gases. All right, so going back to that misconception, so I really need to convince you that it's wrong. We're going to think about nitrogen, N2. So we're going to start with the dot structure for it. No, you will not have to draw dot structures. You don't need to have a panic attack about that. All right, nitrogen's got 5 valence electrons. All right, so we have 3 unpaired electrons, which means we can get a triple bond here, right? I can redraw it a little bit more neatly there too. Okay, now that triple bond, that's really strong and really stable. Both of those nitrogens wanted 3 bonds. They have 3 bonds. This is an extremely stable molecule when we look at the Lewis dot structure for it. All right, nitrogen makes up 70% of the air that we breathe. It doesn't help your body. It doesn't harm it either. It doesn't really care that your body breathes it in and breathes it back out. It's super stable, and because it's so stable, it doesn't have to interact with very much. But it's a gas. So even though it's stable, it's in a really chaotic surrounding. Meanwhile, we've got dynamite, right, TNT, which is crazy unstable. It can explode at any moment, right? But it's a solid, all right? So we have an unstable molecule that's a solid. And then, of course, you have all the other combinations. Stable molecules that are solids, unstable ones that are gases. But the point is that molecular stability and the structure versus chaos thing, they're just not the same thing. You can't use one to determine another. So you can't say, oh, it's exothermic in the forward direction. I guess it will have more entropy in the forward direction too. It doesn't work like that. So now we've got that cleared up. We need to figure out, what are we looking for when we're trying to determine which direction produces, what do you think? Structure, chaos, we don't even know at the moment. We don't know what we're looking for. All right, we know that for enthalpy, we're looking for exothermic reactions, but we need to know what we're looking for here. So think about it for a moment. What do you think we're looking for? Do you think we're going to look for more structure or more chaos as the favored condition for the universe? It's chaos. All right, some of you don't like that right now, but the universe likes chaos. Having stable molecules in a chaotic setting is what the universe has just chosen to settle on. And you don't have to like it, but that's what it is. Gases are by far the most abundant state of matter in the universe. And you think about every time we try to build something, when we try to create structure here on Earth, nature finds a way to tear that down. Right? So the universe tends towards chaos. It's a quote for that. All right, and you can always use this as an argument to try to get out of cleaning your room. It's not going to work, but making your parents laugh during this time is worth something, right? So how do we analyze for this? What are we looking for? All right, we're looking for the direction that produces more chaos, the forward or the reverse direction. And we're going to do that by just looking at the states of matter. So on this slide, all right, I'm not really paying attention to even what the molecules are. I'm saying, okay, over here I've got a liquid, and over here I've got gases. All right, it helps to kind of visualize this too. If we think what a liquid looks like, all right, we've got our liquid down here, versus just all gases, right? Here's all gases. We can see, right, if we sort of visualize it here, all right, that we're going to have more chaos in the forward direction all right, versus having some structure, we would go in reverse. So we would say here that the forward direction, all right, produces more chaos. Okay, forward direction produces more chaos. So that would be preferred by nature. Got a few more examples to take you through. All right, if we look at this one, again, we have solid, and over here we've got solid and gas. So there's a little bit of solid on both sides, but only one side has a gas. So if we visualize that, all right, we start off with just structure. It's all that is over on the reactant side. But on the product side, we have some structure and we have some chaos. Saying which side has, oops, it's a weird S, sorry, has more chaos, right? The product side. So this would also mean the forward direction produces more chaos and would be preferred by nature. All right, now let's take a look at this one. We have all gases over here and over here. Everything's a gas. Both sides of this reaction are just chaos. So we're not going to count the number of reactants versus products. We're going to count the actual number of particles here. All right, that's different from just saying, oh, there's two gases versus one gas. What we're saying here is there's 3 gas molecules, right? 1, 2, 3, versus only 2 gas molecules. Okay, pay really close attention to that. Count the total number of particles. You only do that if everything's a gas, right? If all are gases, count the number of particles, not the number of types of gases, but the number of particles, okay? That's going to be important, so make sure you write that down, pay attention to that. All right, now we have to decide which is more chaotic, 3 gas particles or 2 gas particles. Okay. All right, according to the universe, it's going to be 3. Okay, more chaos over here because there are more gas particles. You only do this if all are gases. Okay, so in this case, we would say that the reverse reaction would be favored by the universe from an entropy perspective because the reverse reaction would produce more chaos. All right, a couple more here. On this one, we've got a solid and a liquid, and on the other side, we have a solution and a gas. We haven't talked about where solutions fall in here yet. Solutions are going to be more chaotic than the solids and liquids, but not as chaotic as a gas. So if you like little hierarchies here, there you go. Okay, so that's kind of where aqueous is going to fall in. All right, and again, if we visualize this, a solid and a liquid together, and then at the end of the reaction, we have a solution and a gas in that container, it would look something like this. Okay, there's our solid and a liquid, and then when the reaction is over, we have a solution. All right, try to show a couple different colors there, and a gas. All right, so this side looks more chaotic. More chaos. Okay. So this side looks more chaotic. We would say it's the forward reaction. Okay. All right, I believe this is our last one here. All right, so in this last one, we've got all gases over here, so that is pure chaos. On the product side, we have some chaos, and we have some structure. All right, so hopefully you've got an answer in mind. I'm going to give you some visuals here too, though. Right? Only gas, there's just chaos versus our gas and our liquid on the product side, right? Which has a little bit of structure to it. This one's going to be reverse, all right? Producing more chaos and being favored by nature. So you don't have to pay attention to coefficients unless they're all gases, right? You don't have to pay attention to what the molecules actually are. Doesn't matter. We're just focusing on those states of matter and which side of the arrow, the reactant side or the product side, has the more chaotic states of matter. Okay? So now I want you to complete the second column of the factors that determine equilibrium worksheet and check that. All right, you're focused on the states of matter. In that first column, you focused on which direction was exothermic, but now you're going to focus on which direction has the more chaotic states of matter. You can't use the first column to help you with the second column because they're not related to one another. Okay, so focus on those states of matter. Let me know if you've got any questions.